In this video, we're going to take a look at solving systems of equations using matrices. So by using the inverse of a 3x3 matrix, we can solve a system of three simultaneous linear equations in three unknowns. So let's say we have a 3x3 matrix here, and we define this 3x3 matrix as A. If I've got A here, that's my 3x3 matrix, and we times this here by the 3x1 matrix of x, y, z. We times this here by x, y, and z. And what this would give me here is my system of three simultaneous linear equations. Okay. So this gives me my system here of three simultaneous linear equations. And let's say this is equal here to the vector v. Okay. Then the solution here for x, y, and z. So the solution here for x, y, and z is given as the inverse of the matrix A times by the vector v. So that's A inverse times by the vector v. Okay. And just remember here, the order of multiplication when we're working with matrices is important. So the inverse of A here should be on the left, and then we times that by v. Okay. So when we talk about a system of three linear equations in three unknowns, you also need to be able to determine whether a system is what we call consistent or inconsistent. When we talk about a consistent system, we say that a system is consistent if there is at least one set of values that satisfies all the equations simultaneously. Okay. If we can't find at least one set of values that satisfies all the equations simultaneously, then we would say that the system is inconsistent. Okay. Now we have a few specific cases here that we need to run through. So for the first case here, let's say that the matrix A here is non-singular. Okay, so if A is non-singular, and just remember here, non-singular means that the determinant of the matrix A is not equal to 0. This just means that det A is not equal to 0. Then in this case, what this tells us is that our system of three linear equations here has one unique solution and the system is consistent. Okay. So we have one unique solution. So one unique solution and consistent system. Okay. So that's my first case there. For the next two cases here then, this is when the matrix A is singular. So if A is singular, and remember singular means that the determinant of A now is equal to 0. So det A is equal to 0. Then here we have two specific cases. So the first case is that the system is what we call consistent. And if it's consistent in this case, then we'd say that there is infinitely many solutions. So rather than one unique solution, we now have infinitely many solutions. So in this case here, like we said, the system can be consistent. So the system is consistent, but we have infinitely many solutions. So infinitely many solutions. And then the second case here is that the system is inconsistent. Okay. So the system here is inconsistent. And you might have guessed it, that means that we have no solutions. Okay. If the system is inconsistent, then we have no solutions. So these are the key points here that you need to be aware of now when we're looking at solving systems of equations using matrices. What I'm going to do now is just run through kind of some examples here, just actually showing what it looks like when the planes are actually intersecting. Okay, so we'll pause the video here and let's look at these examples now, showing the planes intersecting and how that corresponds then to the system of equations using matrices. What we can see here then for the first example is we have the case where the matrix A is non-singular. Let me just write that down to begin with. So A here is non-singular. So A is non-singular, so remember that just means that the determinant of A is not equal to 0. So what does this tell us? Well, this is the only case then where we can have a unique solution. Okay, so we have a unique solution. We have a unique solution. And what that also means then is the system of equations is consistent. The system of equations is consistent. Just write that down in full. So what you can also see here is this diagram. I've actually drawn this myself, and you can kind of see why I went into maths rather than art. But hopefully it kind of helps illustrate what's actually happening here. So what I've got here is 3 planes. So I've got planes, say A, B, and C. So let's say A is the blue plane, B is the purple plane, and then C is this green plane here. What I can actually see then is these 3 planes are intersecting at a single point, which is this pink dot here. Okay. And the reason for that then is because A is non-singular, and that leads to a unique solution. Okay. So that's our first example there. Moving on to the second example here then, what I have now is the matrix A being singular. So A here is singular. Now in this case here, we need to look at the diagram. So I've got my 3 planes again. So I've got the green plane, the blue plane, and the purple plane here. And they're intersecting. Okay, so all 3 intersect here. And what I've actually got here is infinitely many solutions. And the reason for that is because the solutions here lie along a straight line. So this line here, that intersects through the middle here, gives us infinitely many solutions. Okay, so what we'd say here then is the system of equations is consistent. Let me write this down here. So A is singular. The system of equations is consistent. The system of equations is consistent. The system of equations is consistent. And in this case here, with these solutions lying along this straight line, we have infinitely many solutions. Okay, so we have infinitely many solutions. We have infinitely many solutions. And we actually have a special name for this. So what we say here is that the planes form a sheaf. Okay, so the planes form a sheaf. It is important that you're familiar with this kind of language here, so that the planes form a sheaf, because sometimes you might be asked to geometrically interpret what's happening with the planes. Okay, and this is quite a nice answer if that is the actual case. Okay, so there we have it. So that's the second example there. So just 3 more examples to look at here, and I've grouped these 3 together because these are all examples of where the system of equations is inconsistent. So again, the matrix A here would be singular. So A is singular here. So that just means the determinant of the matrix A is equal to 0. And like we said, this is an example here of where the system of equations is inconsistent. So the system of equations here are inconsistent. We'll just write this down in full. So the system of equations is inconsistent. And hopefully it's clear from the 3 diagrams here then that there are no solutions to any of these 3 cases. So the first 2 examples here are examples involving parallel planes. So in this case here, this would be 3 parallel planes. And this example here would be 2 parallel planes. So the purple plane here and this light blue plane here behind. And then this example here is where we have no parallel planes, but what we can see then is around no points here in the diagram where all three planes are satisfied. Okay, so like I said, these three here are all examples then of where the system of equations is inconsistent, because obviously parallel planes can't intersect like we can see here for these two. This one here has no point where all three intersect. Okay, this one here is also an example then of where the planes form a prism. We can kind of see it here, this prism here. It's kind of hard to see from my diagram. A slightly neater diagram makes it a little bit clearer. But again, the system of equations is inconsistent, and again, there would be no solutions. Okay, so let me just make a note of that as well underneath. So following on from that then, no solutions. Okay. And there we have it. So that runs through the 5 cases that I wanted to quickly show, demonstrating kind of where the planes intersect and what that would lead to in terms of a consistent and inconsistent system. So what we're going to do now is just take a look at some practice questions here for solving system of equations using matrices. Starting off here then with the first example, we're asked to use an inverse matrix to solve the following system of equations. I've got my 3 equations here below. I've got x plus 2y minus 3z equals 1. I've got 3x plus 2y minus z equals 3. And then finally 3x plus y minus 3z equals 2. So to begin with here, what I want to do is form a matrix equation. So for the matrix equation here, we're going to have a 3 by 3 matrix. We then multiply this here by a 3 by 1 matrix. And within this 3 by 1 matrix here, this contains the unknowns that we're looking to solve for. So that's x, y, and z here. So the variables that we're working with within the system of equations. And then on the right hand side here, this would be v, our vector v. But v is just a 3 by 1 matrix, and that contains the values here on the right hand side of the equation. So that would be 1, 3, and 2. So 1, 3, and 2 there. So what goes in the 3 by 3 matrix here? Well, that's just the coefficients here of the variables. So x, y, and z here along each row. So for the top row, then that would be 1, 2, minus 3. So 1, 2, minus 3 there for the top row. For the middle row here, then that would be 3, 2, minus 1. And then finally for the bottom row here, that would be 3, 1, minus 3. Okay. So what we're looking to do now is solve for x, y, and z here. And we can easily solve for x, y, and z here by calculating the inverse of this matrix here. And then we're going to multiply that by this matrix here. So what we're going to get here then, for x, y, and z, is like we said, we need the inverse of this matrix here. That's going to be equal then to the inverse of this 3 by 3 matrix. So 1, 2, minus 3. 3, 2, minus 1, and finally 3, 1, minus 3. We need the inverse of this matrix here, and then we times it by this 3 by 1 matrix here. So 1, 3, and 2 there. Now just a point to make here, the inverse of this 3 by 3 matrix, you are just basically expected to use your calculator to find this. If not, you're going to have to do this by hand, and it is quite a lengthy process, and it does take quite a bit of time. So basically what I'd recommend is using a calculator that can find the inverse of a 3 by 3 matrix for you. Now that doesn't mean you need to be able to, or basically that doesn't mean that you can get away with not being able to do it by hand. Because sometimes you might have a algebraic term within the 3 by 3 matrix, but for these types of questions, you'll always be working with a numerical matrix like this, which you can easily calculate the inverse of by using your calculator. So use your calculator here to find the inverse of this 3 by 3 matrix. And if you do all this correctly then, what you should find for x, y, and z here. So x, y, and z. This is equal then to 3 over 4. I get 3 over 4. I get 1 over 2, or a half. And then finally 1 over 4. So in other words, x is equal to 3 over 4, y is equal to 1 over 2, and z is equal to 1 over 4. So let's just write those solutions down. So x is equal to 3 over 4. Y is equal to a half. And then finally, z is equal to 1 over 4. Okay. And there we have it. So we've used an inverse matrix there to solve the following system of equations. So that's the solution there to question 1. And if we work through one more example here, then we've been given 3 planes. So I've got the planes A, B, and C, and they're defined as follows. So we can see the equation here of each plane below. So the plane A, the plane B, and the plane C. So the question says, by forming and solving an appropriate matrix equation, show that the 3 planes intersect at a single point and find the coordinates of that point. So to begin with here, like the question says, we're going to form the appropriate matrix equation. So we have a 3x3 matrix. So don't forget, the 3x3 matrix here is the coefficients of x, y, and z along each row. That would be 1, 1, minus 1 for the top row. So 1, 1, minus 1 there. For the middle row here, that would be 3, 2, minus 5. And then finally for the bottom row here, that would be 1, minus 1, and 1. So 1, minus 1, and 1 there. We then times this here by a 3x1 matrix. And within this 3x1 matrix here, this is the unknown that we're looking to solve for here, or the unknowns that we're looking to solve for. So that's the variables, so x, y, and z here. And then this is equal here to, again, a 3x1 matrix. And these values here are given as the right-hand side of my 3 equations. So 1, minus 2, and minus 3. So that gives us the appropriate matrix equation there that we need to go on and solve this question. Now, before we actually solve this matrix equation here, what we need to do is, like the question says, show that the 3 planes intersect at a single point. So if the 3 planes intersect at a single point, then I know that there is a unique solution here, okay, for x, y, and z. And we know that the only time there is a unique solution is when the matrix A here is non-singular. So what I need to do is find the determinant here of this 3x3 matrix. So if I call that matrix A there, I now need to find det A. So let me just define this here. So A is equal to this 3x3 matrix here. So that's 1, 1, minus 1, 3, 2, minus 5. And then we've got 1, minus 1, and 1. So what I need to find now is det A. Now, again, we simply just need to use our calculator here. You can do it by hand, but again, it's just, it takes up a bit of extra time where you can simply just use your calculator to do this. So if you put this into your calculator here, this 3x3 matrix, and then type in det A, that would give you the determinant then of this 3x3 matrix. And what I get here is minus 6. Okay. So what I've got here is a matrix A, which is non-singular. So therefore, A is non-singular. So A is non-singular. And in that case, then when we get a matrix A like this, which is non-singular, that means that there is a unique solution. So a unique solution exists. Okay, so just making that clear there. So that's the first thing that we need to do there. So just show that the 3 planes intersect at a single point. So what we need to do now is actually find the coordinates of that point. And to find those coordinates, what we're going to do here is solve for x, y, and z. So to solve for x, y, and z here, what we're going to do is calculate the inverse of this matrix here and times it by this 3x1 matrix here on the right-hand side. So in this case then, for x, y, z, this is equal then to the inverse of this 3x3 matrix here. So I've got 1, 1, minus 1, 3, 2, minus 5, and then finally 1, minus 1, and 1. So we need the inverse of this matrix here. Then we times that by this 3x1 matrix here. So 1, minus 2, and minus 3 there. Okay. And again, we're just going to simply use our calculator here. If you can't use your calculator to do this, again, you have to do this by hand. It just takes a bit longer to do, but it is absolutely fine to just put this into your calculator here. So therefore, what we get here for x, y, z. So for x, y, z here, what I'm going to get then is I get minus 1, I get 3, and I get 1. Okay, so what that tells us then is that x is equal to -1, y is equal to 3, and z is equal to 1 there. Okay, and there we have it. It's like as the solution there. The very last question. That brings the end of this video on solving systems of equations using matrices.